Hello everyone, my name is Amir Amini. Hope you are all doing all right and safe. I'm gonna present our work entitled Dynamic Event Triggered Formation Control for Multi-Agent Systems with a focus on co-design approach. So formation, as we know, is one of the cooperative behaviors in multi-agent systems. As we can see in the figure, there are 4 agents starting from initial conditions. The objective is to form them a predefined geometric pattern, which in this case is a square. So in the work, we consider general linear multi-agent systems. Xi is the state of agent I, A and B are system matrices, input matrix, known and constant. Ui is the distributed control protocol, and N is the number of agents in the multi-agent system. We consider that A and B is a controllable pair, and also the communication network is undirected. So what is really the definition of event-triggered formation? We say that for given formation vectors Hi, we should first design a distributed protocol Ui and at the same time a distributed transmission scheme. The transmission scheme does not allow constant time transmission. It only allows transmissions based on some certain situation. And the objective is to have the disagreement between any states of agents should be equivalent to the disagreement between Hi and Hj, right? It is similar to the consensus definition if we assume that Hi is 0. So assuming that Hi is 0 for all agents, formation is reduced to consensus. And hopefully by different choices of formation vectors, we can control the steady state formation, okay? So here is a block diagram of event triggering implementation. Denote T0, Ti, T1i, Tkii as the event sequence of agent I. With this definition, Xi, Ti, Ki is the most recent state value of agent I. Let's start from somewhere here, for example. Agent I produces some states, Xi. It goes to a block called event detector. The event detector also receives the states from neighboring nodes. The event detector has some condition thresholds, and it comes up with 2 decisions, either 0 or either 1. If the decision is 1, we say that an event has been detected. So we update our previous event to the real-time state value. We also transmit it to the neighboring nodes, and we also send a version to the local controller. On the other hand, if the decision is no, we say no event has been detected, so we don't transmit to neighbors, and we just continue our previous loop based on the previous event value. So this is like a general framework of event triggering implementation. We define a vector called Qi, event-based disagreement vector. It takes into account the disagreement between the recent event at node I and recent event at node J. Also the disagreement between their corresponding formation vectors. The control protocol considered in this work is a state feedback 1, which is based on Qi, the event-based disagreement, and 1 unknown control parameter K. So we should design K. The transmission threshold is a dynamic event triggering one. It basically says that starting or knowing the previous event instant, the next event instant is triggered as soon as this condition is satisfied. So the condition is based on some unknown parameters, S1, S2, S3. We should design them. It has a parameter called measurement error, is the difference between the real state value, the real-time state value, and the most recent event instant. We also see Qi. Qi was the disagreement vector. We saw it before. And we see something new, eta I. Eta I is a dynamic threshold, and it satisfies this equation, the first order differential equation. S4 and S5 again are unknown. we should start at I with a positive value, and Qi again is the disagreement vector that we know. So hopefully we are expected to see a higher value of threshold in the right-hand side of 4. So we can hopefully reduce the number of transmissions even further. So there are some good things about the dynamic event triggering. First, we noticed that it is a powerful transmission scheme as compared to its counterparts. Fortunately, it does not produce a steady state error in the formation. And we can observe that many traditional transmission schemes are like special cases of DET. For example, the very well-known threshold, which is based on a set valued and exponentially decreasing term, is a special case of DET, and also the state-based scheme, transmission scheme, is also a special case of the DET. So, however, there is one complicated thing about DET, which is the multiple unknown parameters that we should design. So we have to design more unknown parameters, which may make the design stage more complicated. When it comes to the matter of design stage in event triggering schemes, we have two different approaches. One of them is emulation-based, the other one is the co-design. In emulation-based, first we assume that real-time transmission is possible. So we just ignore the event triggering transmissions. Based on this assumption, we first design the control parameter. And as the second step, knowing the control value, we design the unknown parameters for event triggering. On the other hand, in co-design, we design all unknown parameters simultaneously. As we can expect, there are advantages and disadvantages attached to each approach. But one interesting thing about the co-design approach is that we can include performance objectives such as H-infinity optimization, L2 optimization, or maximizing the inter-event time. So in this work, we focus on co-design approach. The objective of this work is first to have an exponential rate for the convergence of formation, increase the inter-event time, or equivalently try to reduce the number of transmissions as much as possible. Mathematically, we can see that smaller values for K, S1, and S4, and larger values for S2, S3, and S5 can lead to fewer number of transmissions. So we can see that there are some trade-offs. We can imagine that there are trade-offs between the formation convergence rate and intensity of the event triggerings. And we came up with the idea of having a co-design optimization that can handle the trade-off, this trade-off, and hopefully reduce the number of transmissions. So like in any other control problems, we should derive the closed loop system. The closed loop system is based on X and E and H, an additional term again with formation vector. We use a state transformation to convert formation problem to a stability problem. Here we use the eigen decomposition of the Laplacian matrix. So here W is the eigenvector matrix, J is the eigenvalue matrix, and we use the formation psi, which uses W tilde, and W tilde is like closely related to W inverse. So if we use this transformation, we come up with system 8. System 8 is based on psi, E, which is the measurement error, and H is the formation vector. So it is possible to show that a stability of system 8 is equivalent to having formation being achieved. So it's like a bidirectional statement. So we focus on stabilizing system 8. But we see one additional term here, which does not depend either on E or psi. We come up with a necessary condition called, also known as the formability condition in the literature. It says that, okay, we have to get rid of this term, and we should make sure that this term is made 0. So A plus B, H times hi formation vector, it should satisfy this equation and they should basically be zero. The physical interpretation is that by only using a state feedback, we cannot expect to achieve any desired formation for any general linear multi-agent systems. So this is a necessary condition. So we go on and continue with Lyapunov stability, do necessary derivations, manipulations, and using some semi-definite programming techniques, we come up with this optimization. So there are really so many details involved here. I only focus on the big picture. There are some decision variables, P, S1 tilde, S2 tilde, some positive scalars. There is one desired or initial or given parameter. I name it desired convergence rate, zeta. So this is one given parameter. This is the convex optimization problem. We can solve it using like LMI lab in MATLAB or different packages. So once we solve this optimization parameter, we can simultaneously compute all our unknown parameters, the control gain and DET parameters. So what does the objective function basically doing? It tries to increase S2, S3, S5 and decrease K, S1 and S4 with the hope of reducing the expected transmission. And the approach is a linear weighted sum. So we apply some slack variables and connect them with S2, S3, S5 and other parameters, and we come up with an optimization function, objective function, so that these parameters are increased and the other parameters are decreased based on the linear weighted sum. And another thing is that this optimization guarantees an exponential rate for psi, for stabilizing psi, and also the event triggering threshold. So we can say that formation can be achieved exponentially fast. Let's do one experimental examination here. We consider 5 unmanned aerial vehicles with the state equation, the nonlinear 6 state equations here. Fortunately, UAV 14 is feedback linearizable to 3 independent double integrators, XI, XYI, with just new control inputs AX, AY, AH. We can imagine that there are some big relationships between AX and the actual states of the system, which I just ignored it for presentation here. We consider a 5-ring network, which has a Laplacian matrix of this form. The objective is to have the UAVs form a regular pentagon. How to choose HI? Again, we don't jump into details, but we can say that by appropriately choosing HI and wisely choosing them, we can make sure that this formation of UAV can be achieved based on the regular pentagon. The initialization parameter is zeta 0.2, and we can solve that optimization parameter and compute unknown parameters at the same time simultaneously. We do the simulation and get these figures. In this figure, we see that the UAVs start from initial condition and ultimately they form a regular pentagon here. So this is the figure of transmissions, the transmissions for 7 seconds, like are in the order of 50s, 60s. This is also the trajectories of the additional threshold eta I. We can see it starts from initial condition, like for example 1, it rises, and then once the formation is about to achieve, it approaches 0. So we can see that eta I really, when it matters during the procedure, it adds a relatively high amount of threshold. So, and it's basically useful in reducing the number of transmissions. Let's see the impact of the desired convergence rate zeta. We make a table, incrementally increase zeta from 0 to 0.3. There is T star, which is the formation termination point when formation is achieved, and AIET, average inter-event time. So once we increase zeta, T star is being reduced. That means formation is achieved faster, but that is at the expense of more intensity for transmission. So we can say that Zeta is really capable of having a trade-off between the formation, convergence rate, and the intensity of the event triggering. All in all, we propose an implementation that can guarantee formation with the desired exponential rate, and we use dynamic event triggering, which was a powerful event triggering scheme. The design stage was based on the co-design, and we could simultaneously design all unknown parameters based on the convex optimization. And we could see that the trade-off between formation, convergence rate, and intensity of transmissions was handled by the optimization. So that's the end of presentation. Thank you for your attention. If you have any questions, I would be glad to answer.